All right, so here's example 2 in our chapter on forces, chapter 6. Um, we've talked about how Newton's second law tells us that the net force on any object, so that the sum of all the forces, if there's more than one, equals the mass of that object times its acceleration. And of course, that force, don't leave much room up there, that force and that acceleration are going to be in the same direction. You can't apply a force east and have something go west. Of course, that object is going to go east in the same direction that you apply the force. So here we have a pitcher applying a force to the baseball. All right, and right here, kind of like we indicated before, he's applying a force that way. All right, but you can think of the ball as being a point mass, and the force coming out like this right here, force on the ball. But either way, it's being applied in, we'll call that the positive direction, because down here, here's our coordinate system, and there's our positive x right there. All right, now a couple of things we want to change here. We have our baseball the mass of it is in metric units, kilograms, okay? 0.15 kilogram baseball. That's good. That's what we want, all right? Kilograms is going to be our units for mass in force problems. But we've got this problem right here. We have this velocity of 90 miles per hour. Well, that doesn't make us very happy because that's English units, all right? So what I'm going to do is I'm going to do us all a favor, and we'll just do the factor labeling of that together. So 90 miles per hour, and we're going to do a factor label together, so just kind of refresh yourselves on this. 1 mile, I happen to know, is 1609 meters. That might be one conversion you might want to commit to memory, because if you are asked problems like this, that's kind of a handy conversion from the typical English miles to metric meters. So we've got miles to meters, so that goes away. And hours, of course, we know 1 hour is 3,600 seconds, and so that'll give us a value in meters per second, which is what? Let's see here. That's 40.2 meters per second, all right? So that's our velocity right here. Now you might be asking yourself, whoa, wait a second. I thought velocity was kinematics. Yes, but we don't have an acceleration here. Remember, our main equation here is force equals mass times acceleration. All right? It's asking us to find the force that the pitcher applies to the ball, but we're not given an acceleration. What we do know is that right here, the ball is at rest, and right here it's at its final speed or velocity of 40.2 meters per second. And so we need to do a little bit of kinematics to find this acceleration that it experiences going from here to here. So then we can find the force. All right, got kind of a plan of action right here. So let's go ahead and do that. It's also important to note that it doesn't accelerate right away, but it accelerates from rest through a distance of 2 meters. So this right here, we could think of this as being our final velocity right there. Of course, our initial velocity over here equals 0 meters per second. So I'm going to go to the next page. I'm going to sort of redraw this here and to make this a little bit cleaner. All right, so the mass of the ball equals 0.15 kilograms. All right, acceleration on the ball, well, we don't know yet, but what we will in just a second. What we really want to find out is the force, or I should say, the net force applied to the ball. All right, now there is only one force, and that's from the pitcher, but there could be other forces, so we equate the net force to mass times acceleration. So let's find the acceleration of the ball. So the initial velocity equals 0 meters per second. All right, and our final velocity equals 40. Oh, I wrote meters per second squared, didn't I? Sorry, meters per second. And our final velocity is 40.2 meters per second. and our displacement equals 2 meters, we should be able to find our acceleration. All right, because final velocity squared equals initial velocity squared plus 2 times our acceleration times our displacement. Oops, and I put my delta but not my x right there. All right, well, let's solve for acceleration. So our initial velocity is going to come over, so it's going to be final velocity squared minus initial velocity squared. And then we're going to divide down the 2 and the displacement. So divided by 2 times the displacement, and that'll give us our acceleration, which is going to be what? 40.2 meters per second, we can say, squared, that's our final velocity, minus, well, that's easy, 0, right, 0 squared, divided by 2 times our displacement, 2 meters, right there. And that gives us, what those guys give us? It gives us 404 meters per second squared. 404 meters per second squared. Now, if we look at that number for a second right here, let's put a dotted line around that, because all that hassle we just went through was really to get the acceleration on the ball right there. That number is a crazy high number, over 400 meters per second squared. If you consider the fact that a g, remember 1 g equals 9.81 meters per second squared, then a baseball is experiencing about more than 40 g's, which is pretty crazy. So it's a lot of force that a pitcher is applying to that ball right there. So, but I'll erase that. I know it's just kind of a little bit of extra trivia right there, but that's a really, really high number. So baseballs are accelerated from rest to a high velocity in a very short period of time. So it's going to require a lot of force. So let's find out what that force is. All right. So the net force on the ball is what we want to find out. And that's what I just wrote right up there. So that's going to be the mass of the ball times the acceleration of the ball, which we just calculated. All right, so that's going to be 0.15 kilograms times 404 meters per second squared. And that gives us a net force on the ball of 60.6 newtons. Now remember, a newton is about a quarter of a pound, so if we were to divide that by 4, so that means that there's about 15 pounds of force that are applied to that ball right there. So anyway, I don't want to get too much into pounds. Let's stay with newtons right here. Newtons is going to be our main unit of measurement, but that's how many newtons of force have been applied to this ball over those 2 meters, accelerating it from rest to having a final velocity, and therefore undergoing an acceleration. So that's example 2 for us, and I'm going to have you look ahead to the next videos for the subsequent examples. So thanks for watching. I'll see you on the next one.